Okay, now let's look at some error checking methods, validation and verification methods. Uh, One of the method is known as parity checking. Then we will look at ParityBlock method, then CheckSum, and then we will discuss the CheckDigit method. Okay, first of all, let's look at what parity checking means. Parity is basically this method involves the use of one parity bit. So basically, if I have one byte of data, only 7 bits of this 1 byte are the actual data, and the remaining 1 bit, either it could be the most significant side, in some examples the least significant side is also being used. But in this particular example, we can see the most significant side will be reserved for the parity bit. Now basically what happens is that against this data, the an agreed parity will be decided upon by the sender and the receiver. So let's just say that both devices decide on an even parity. Then it means that my data transmission that will be sent, this 1 byte when it's sent, should contain an even number of ones. So if I'm deciding on even parity and I want to complete this whole data with the parity bit added, what I will do is that I will add a 0 to this. This parity bit added along with this entire data will reflect the even parity, because as you can see here, I've got a total of even number of ones, 1 2 3 4 4 ones, even parity. Similarly, if I have chosen odd parity with this exact same data, instead of adding a 0 here, why did I add 0 here before? Because already I had even number of ones. So I just added 0, not to change the parity. It's already even. But if I want to make an odd parity out of this data, I will have to add a 1 over here. So basically for an odd parity, I added 1 here. Now I've got an odd number of ones. Whatever parity is chosen, may it be even or odd, it has to be agreed upon by both the sender and the receiver. So what happens is that when I send data, let's just say I'm using odd parity. If I'm sending data, the receiver will make sure the data has not been corrupted in any way on receiving by counting the number of ones. So if I were choosing odd parity, my number of ones will be odd. And if the receiving computer also sees odd number of ones, that means the data transmission was okay. That no data transmission error has occurred. However, this is not always the case. If, for example, I've chosen even parity, this data is sent over here. So, for example, I sent this data even parity. Then I am using even number of ones. The receiving computer will also count even number of ones, and it will assume that data transfer has been carried out perfectly, no error whatsoever. Again, as mentioned before, this is not always the case. What can happen is that if, say, for example, instead of one, if I say 1 bit changed around, so if, for example, this data is sent with even number of ones and 1 bit became 0, 1 became 0, so this became 0 right here. So my data will look like this. So I changed this to 0. Because of this, my receiving computer now sees odd number of ones. Agreed parity was even, receiving computer sees odd number of ones. Therefore, it will identify this as an error and immediately cancel out this data, and it will request for retransmission. However, if, say, for example, instead of changing 1 bit, 2 bits changed. Now, I agreed upon even parity. My receiving computer also received even parity, even though 2 bits changed. My receiving computer would also still see an even parity. It was 4 before, now it sees 2 ones. Even parity before, even parity now. And will simply say the data is okay. However, it's not okay. Not 1 bit, in fact, 2 bits changed. So what that means is that even parity will not work if an even number of bits change, 2, 4, some stuff like that. In this case, you can see 2 bits changed. Same thing is here. If you say this data was transferred using odd parity, and I changed 2 bits here as well. As you can see here, I changed 2 bits and my receiving computer will still see odd number of ones. And therefore it will assume the data is okay, even though 2 bits changed. So even number of bits changing May it be a transposition error? Transposition error means that this one came here and this one came here, even though this number of ones did not change, but actually data did change. So if a transposition error occurs or even number of bits change, then the parity does remains unchanged. And because of which the receiving computer will not be able to identify if the data is corrupted or not. So that's one of the drawbacks of parity. But if that does not happen, even number of bits don't change, odd number of bits change, then the receiving computer will very easily identify whether or not something went wrong. Now, another method is known as parity block. So instead of sending one byte, you send multiple bytes. Now, the parity block method happens in this way is basically you should be, if applied correctly, you should be able to identify what bit exactly went wrong. So as you can see here, I'm transferring these 9 bytes and there's another parity byte away. So to identify, I sent a collective, this data is sent in one whole block. Now the receiving computer and an even parity has been decided upon before sending, between the sender and receiver. Now, I sent this entire block of data. The receiving computer will analyze this data, even parity for even parity. Now, what the receiving computer does is, first of all, it looks at the individual bytes. I got byte 1, 2, 3, 4, 5, 6, 7, 8, 9. Each byte, and even this one as well. It will look at each byte. As you can see here, 1, 2, 3, 4, 5, 6. We got even here. 1, 2, 3, 4, even here as well. 1, 2, 3, 4, 5, 6, even here as well. So all of these bytes are still following even parity as agreed. However, byte number 8, as you can see here, 1, 2, 3. There's something wrong with here. This byte is not okay. It has shifted from even to odd parity. So my receiving computer has capably identified that byte 8, there's something wrong in byte 8. Now let's start looking bitwise. 1, 2, 3, 4, 5, 6. Okay, that's still even. 1, 2, 3, 4, still even. 1, 2, 3, 4, still even. This is also even. But however, bit number 5, as you can see, 1, 2, 3, 4, 5. So there's something wrong with bit number 5. So this is not even parity. This is odd. This is odd. So by that logic, my receiving computer has reached the conclusion that bit 5 of byte 8, it has been compromised. So not only is this an error detection method, it can also be used for error correction as well. Now I categorically pinpointed that byte 8, bit 5 is wrong. So if you convert this, if you turn this back to 0, your data may be correct. So this is a very good technique for both identifying the error and possibly correcting it. This method only allows for error detection. This allows for detection as well as correction. Now there's another method that can be used, which is also known as CheckSum. A CheckSum, very simple technique. The procedure for CheckSum goes in this way, that I have some data that I want to send. You make use of a formula to calculate some value on this data. So I take a block of data and apply that formula on that whole block of data. And because of which I will end up with a numerical value. This numerical value is the checksum. I will attach that checksum at the end of my block of data, and I will send the data. The receiving computer will separate the checksum on receiving from the actual data. The receiving computer will then apply the same formula that the sender used to try to recalculate the checksum on the block of data. The receiving computer will then end up with a sum of its own. If the calculated sum on the receiving side is the same as the sum it received, then that means there is no data corruption. However, if both values differ, that means the checksum technique has identified an error in the data transmission, and therefore this receiving device will notify the sender to retransmit the data because there is an error. So just a quick recap, the sending computer applies a formula on the data, a block of data to calculate a checksum. The checksum will be added to the actual block of data and forwarded to the sender, to the intended recipient. The recipient will separate the checksum from the actual data, recalculate the checksum on its own side using the same formula on the block of data. It will end up with a checksum of its own. If its own calculated checksum is the same as it was received from the original transmission, then that means the data is okay, can be trusted. If both sums differ, then the retransmission will be required. Following this, we have another method that is known as CheckDigit. Now, CheckDigit verification basically identifies errors such as, for example, there is an incorrect digit entered, 5327 was supposed to be entered, but sorry, 5307 was supposed to be entered, but I entered 5327. And it could be also a transposition error. For example, 5037 was supposed to be entered, but 5307 was entered, or sorry, 5307 was supposed to be entered and 5037 was accidentally entered. You see, 30 and 03 have been transposed here. Similarly, I'm missing a digit, 537 was entered, or 53107 was entered, 53 instead of 5307. So, errors like this, or it could also mean a phonetic error that the misheard term 13 was supposed to be entered, or 30 was supposed to be entered and was misheard as 13. So 30 and 13, they sound similar. So errors like these can be identified using a check digit. Now we have two methods for check digits. There is the ISBN 13 method and the modulo 11 method. ISBN 13 method simply, regardless of whatever method you're using, both methods allow for two steps. First step is the check digit calculation on its own, and the second step is the check digit verification. Now, both of them allow for this. Now, let's look at the ISBN 13 method. By the way, ISBN is the international book number that is simply used to identify different books internationally. So these are basically 13 digits, and each digit is identified sort of like this. So for example, I have an ISBN number 9780340983882. Now to make this ISBN, you notice that this does not have the check digit yet. Now, again, as mentioned before, for check digit verification, we need the first step to calculate the check digit. We only have 12 digits here, but to add the 13 check digit, we have to do this process. Now, what happens in ISBN 13 method is that I take the odd digits separately and the even digits separately. Digit number 2, 4, 6, 8, 10, 12, odd numbers 1, 3, 5, 7, 9, and 11. So we take the odd numbers first, odd digit places first, and simply add them. So I added 9830888 to get 36. And then we take the even numbers and add them as well. 704932, resulting in this number. And the difference is for the even numbers, I have to multiply by 3 as well. We get the number 75. Add these two numbers together, 75 plus 36 becomes 111. Divide them by 10, you'll end up with 11 remainder 1. We take this remainder and subtract it from 10, you end up with 9. This will become your check digit. Attach this to your number and forward it. So as you can see here, this is my complete number. Now, this number will be used in its entirety. Just to make sure that the number was entered correctly, this check digit can be used to verify if the number was correct or not. How? Now, same step. I've got the complete ISBN, the 13-digit ISBN, including the check digit here. I will separate the odd numbers versus the even numbers. Odd numbers now become 98308, and 9. 9830889. Add them together, we'll get 40. Take the even numbers 70492. Add them together, multiply them 3, same as before, get 75. Add them together again, divide by 8. This time your remainder should be 0. If your remainder is 0, that means this number is correct according to this check digit. And there has been any such of error, such as, transposition or phonetic or missing a digit, so and so forth. None of these such errors. How did I verify it? Because the recalculation along with the check digit, divide by 10, remainder 12, remainder 10, sorry, divide 12, 120 divided by 10 is 12, remainder 0. If I am getting a recalculation remainder 0, that means the number is okay. If I don't get a remainder 0, that means the check digit has identified a possible error in this number. Now let's look at the modulo 11 method. Is again similar. Now modulo 11 allows for these digits. Say for example, I've got the digits 0, 1, 7, 6, 5, 1, 4. So as you can see here, these are total of 7 digits, starting from 2 to 8. 2, we will label each digit with its position. So as you can see here, starting from the right, this one digit is missing over here. Place number 1 is missing. That will be my check digit. Apart from this check digit, the second place is 2. This is 3, 4, 5, 6, 7, and 8. So these are the place values starting from the right of these numbers without the check digit. When I add the check digit, that will be placeholder 1. That will be place 1. So right now, without the check digit, I'm starting off with 2, 3, 4, 5, 6, 7, 8, 0, 1, 7, 6, 5, 1, 4. The next process is I will simply multiply. This is my number. I will simply multiply each digit of this number with its respective position value. 0 multiplied by 2, 1 multiplied by 3, 7 multiplied by 4, 6 multiplied by 5, 5 multiplied by 6, 1 multiplied by 5, 7, and 4 multiplied by 8. We get 4 multiplied by 8, 32, 7, 30, 50, 30, sorry, 30, 28, 3, and 0. Add them together, get a total of 130. After that, I will divide the total by 11. I will get a number 11, remainder 9, because 11 times 11 is 121, but that's why I get a remainder 9. So once I get this remainder 9, I'll subtract that from 11 and get a number 2. This will form my check digits. Now, if my resulting, so for example, if I get a remainder 1 here, that means I will subtract 11 minus 1 and I'll get 2 here, sorry, 10 here. If I have a remainder 1, 11 minus 1 results in the check digit being 10. I'm not allowed to add 10. So if I end up getting a 10, I will simply use the letter X for that. That's the method used for that. So if I am getting a remainder X, so if I'm getting a check digit 10, I will call that an X. But other than that, I can simply mention the check digits that I get by the subtraction of the remainder from 11. If it's 10, I will write X. Apart from that, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 can be mentioned like so. So added this check digit along with the original number added here makes my complete number. Now, as mentioned before, the first process is the calculation of check digit. The second process is verification. Now, how do I verify? Simply, this time around, I will also use the check digit with its respective position value, which is 1 in my calculation. So 2 multiplied by 1, 0 multiplied by 2, 3 multiplied by 1, 7 multiplied by 4, 6 multiplied by 5, 5 multiplied by 6, 1 multiplied by 7, 4 multiplied by 8. Add them together, you will get a total of this. This time around, when I divide this by 11, I should have no remainder. Just like before, I should not have a remainder. I should not have a remainder here either. So if I'm ending up with a remainder, that means there is something wrong with this number here. There's something wrong with this number here because this check digit does not add up with this one. There's something wrong with this number. So if I'm getting a remainder 0, that means the number is okay.